Welcome to the Introduction to Geographic Information Systems and Science lecture series developed by the Quinney College of Natural Resources at Utah State University. Discussion topics for this lecture include coordinate systems and projections. Coordinate systems and projections are truly the crux of geospatial observations and measurement. These mathematical interpretations of location allow us to take measurements from a three-dimensional sphere, such as the Earth, and project those measurements onto a two-dimensional flat map for analysis. Before we delve into a discussion about projections and coordinate systems, let's briefly review the basic geographic elements: location, attributes, and time. Location is required by an object or an event to be considered a spatial element. Attributes are necessary to describe a measured or observation of an event or value at a location, and time, while not always required, provides the temporal component to some attribute measurement. Beginning with some different types of geolocation methods, we'll start with talking about places and names. Places and names have been used for millennia to describe a location. It's a simple method of geocoding. So if I ask you the question, how many of you have been to Paris? And you think, well, I've been to Paris, France, and I didn't qualify that with Paris, Idaho, you could have confused the two locations. Names are not necessarily unique, thus they must be used carefully to avoid presenting confusion. Other measurement systems can be very specific to a certain location. The United States Public Land Survey System, or PLSS, evolved out of the need to survey and distribute land resources in the western United States in the 1800s. This system was based on a principal meridian, a baseline, 6-mile rows parallel to the baseline to form townships. Blocks were laid out in 6 by 6 mile ranges. 36 1-mile by 1-mile sections were laid out inside each township and range block, and each section was divided into 4 quarter sections of 1/4 square mile, which was the size of a family homestead. This was extensively used in the western United States, but has no real application outside of this region. Other geolocation systems are postal codes, IP or Internet Protocol addresses, linear referencing systems, and other cadastry-type systems used for surveying. It's important when we're measuring location on the surface of the Earth and representing that on a two-dimensional map that we use the systems that have the ability to provide the most appropriate spatial resolution and locational information for our area of interest. Coordinate systems provide regular and consistent methods of quantifying location, as opposed to something like the Public Land Survey System or using place names. We have two types of coordinate systems that allow us to apply measurements on a sphere or a plane. These are the geographic coordinate system and the projected coordinate system. A geographic coordinate system allows us to apply measurements on a three-dimensional sphere, such as the surface of the Earth, using angular units of degrees. Projected coordinate systems, on the other hand, allow us to apply measurements to smaller areas, generally using a Cartesian coordinate system, which we'll discuss, to smaller areas and simplify calculations. These PCSs are two-dimensional systems that use varying units of measure, such as meters, feet, inches, and so on. The geographic coordinate system is a method for describing the position of a location on the Earth's surface using measures of latitude and longitude. Geographic coordinate systems require a datum, a prime meridian, and an angular unit of measure. Latitude and longitude were developed, or rather discovered, as a method of comprehensive global geographic coordinate system measurements. Longitude and latitude coordinates are made up of intersections between lines of latitude and longitude. Latitude measures degrees north and south of the equator, while longitude measures degrees east and west of the prime meridian. Latitude is an angular distance between the plane of the equator and a line passing through the point under investigation, or our point of interest, and the center of the Earth. Likewise, longitude is an angular distance between the prime meridian and the meridian of the point of interest to us. One misconception is that the Earth is a perfectly round sphere. From space and the pictures that we see from satellites, indeed, the Earth looks perfectly round. But actually, it's more of a spheroid or an ellipsoid shape that's been squished, for lack of a better term, along its equatorial axis. So the Earth as a spheroid, or a squished sphere, requires that we understand what those values of the minor axis and the major axis, or the semi-minor axis and the semi-major axis, happen to be. These measurements, essentially measuring from the center of the Earth have been done numerous times by different people. In 1866, Clark measured the semi-major axis at 6,378,206.4 meters. If we contrast to the geodetic reference system of 1980, which was measured using satellites and the gravitational center of the Earth, the semi-major axis was measured to be 6,378,137.0 meters. So if you compare and contrast those values that were measured in 1866 versus 1980, there wasn't a whole lot of change, stating that we can actually do a very good job with minimal technology making these measurements. However, as time has improved, so has our accuracy, and this better measurement of the semi-major and semi-minor axes has given us the ability to be more precise in our measurements. When we're talking about the semi-major and semi-minor axis, and we reference the center of the Earth or the Earth's gravitational center, we need to talk about a geoid. Geoid is a model describing the form the Earth's oceans would take if there were no land and the water were free to respond to gravitational and other forces. So if we take a look at NASA's GRACE satellite measurements, you can see different gravitational anomalies, where gravity is acting as a stronger force or a weaker force across the surface of the Earth. Here's another example showing global variations but in meters using the WGS 84 geoid height. Note there are substantial variations around the globe. Moving on in our conversation about projections and coordinate systems, we need to discuss the datum. Now, a datum provides a frame of reference for measuring locations on the surface of the Earth. Really, it defines the origin and orientation of latitude and longitude lines. Any given datum is only valid for a localized area or region for which it is designed. So datums are incredibly important and allow us to conduct more accurate measurements at smaller locations. So due to variations between actual topography and models of the Earth's surface, there's a need for more complex, localized adjustments, which is why we use a datum. As a spheroid approximates the Earth's shape, the datum defines the position of the spheroid relative to the Earth's center. So in the upper right, you can see the slide showing the actual topographic surface, the ellipsoid surface, and the geoid surface. And the datum allows us to find the differences relative to the Earth's center. Two most commonly used datums in the United States are the North American datum of 1927, which I should note is depreciated and generally no longer in use, was based on the spheroid Clark 1866, which we discussed briefly, and used Mead Ranch, Kansas as its place of origin. On the other hand, North American datum of 1983, or NAD 83, is based on the spheroid GRS 80, which we also discussed, and uses Earth's center of mass as its origin. Finally, a worldwide datum used by the GPS systems, in fact all GPS systems that are in orbit, is the World Geodetic System of 1984, or WGS 84. Similar to NAD 83, but this is optimized for global accuracy and is generally used by military applications or global positioning systems. As a side note, these datums are often available for setting in a handheld GPS unit, and it is always important that you understand what your datum and your coordinate system are when using a GPS, because the combination of the wrong coordinate system and datum can give you erroneous location readings. So, measuring with GIS. Measuring with latitude and longitude on a consistent basis would be difficult. We can't always carry around a globe in our pocket and show somebody where we are using latitude and longitude. Thus, map projections have been developed to simplify spatial measurement, especially at localized scales. So a few terms to remember. Geographic coordinate system is an angular location reference system on a sphere, such as latitude and longitude. A spheroid is a mathematical model of the shape of the Earth. And a datum is a localized point of origin for measuring, defining the position of the spheroid in relation to the Earth's center. All three of these terms are very important to remember as we continue our discussion about projections. So how is a projection different than a coordinate system? Well, really, a projection is a method for making a three-dimensional globe into a usable flat map. To simplify local measurements, we project the ellipsoid onto a two-dimensional plane using a Cartesian coordinate system to describe XY locations. The coordinate grid has the advantages of consistent lengths, angles, and areas across these two dimensions. So projected coordinate systems require three things: a geographic coordinate system from which it is based, a projection, and projection parameters. So thinking back to your days in geometry, a Cartesian coordinate system essentially has an origin value of 0, 0, and as we move away from the origin, either in the positive or negative directions, we have different xy locations on that system that let us know where we are. Projected coordinate systems are always based on a geographic coordinate system. Now don't let that confuse you. We use the two in tandem. A projected coordinate system must have an underlying geographic coordinate system in order to be properly projected. So if we talk about projection parameters from ArcGIS, so recall, in addition to needing a geographic coordinate system, a projected coordinate system needs projection parameters. These projection parameters can generally be defined by looking at the projection information for a geospatial file. Note the different projection parameters starting at the top. The projected coordinate system always has a name. In this case, we're displaying USA Contiguous Albers Equal Area Conic USGS version. The name of this projected coordinate system, USA Contiguous Albers Equal Area Conic USGS version, suggests that this coordinate system should be used for the continental or contiguous United States. It's Albers equal area, it's a conic projection, and it's used by the USGS. The projection obviously is Albers. There are no false easting or northings associated with this coordinate system. The central meridian of the coordinate system is negative 96 degrees or 96 degrees west. The standard parallel is 29.5, the second standard parallel is 45.5, and the latitude of origin is 23 degrees. Note the last item is the linear unit of measurement, in this case meters. The next four lines define the geographic coordinate system, the datum, the prime meridian, and the angular unit of measurement of the geographic coordinate system. So what is a map projection really? Well, if you imagine taking a globe, a translucent globe, putting a light bulb inside of that globe, and in a dark room you turn that light bulb on. The light projecting out is going to project or display on a flat wall or surface the curved features from within the globe. Now depending on where you put that light, you'll notice different types of distortion. Just like if we look at a standard map of the world, generally speaking, the equator has very little distortion, and as you move away from the equator, your distortion increases. The bad news about map projections is that they are all distorted. To some extent, all projections suffer from loss in conformality, or an angular measure, distance, direction, shape, scale, and area. The good news, on the other hand, is that distortions are predictable. It is possible to design different projections that preserve one or more of the elements that we previously mentioned, depending on the need that you have when you're making your measurements. And here's a few examples. We have true direction projections, Mercator stereographic, conformal projections such as Lambert's, polar stereographic or UTM. We have equal area projections such as Albers and sinusoidal, and we have equidistant projections such as azimuthal, equidistant, and simple conic. So once we project the spheroid onto a two-dimensional plane, we can use a Cartesian coordinate system to describe XY locations. The coordinate grid has the advantages of consistent lengths and angles and areas across the two dimensions, allowing for simple measurements such as Euclidean distance and analytical geometry. So when we talk about projections, we need to talk about tangency. Projections are most accurate at the point or line of tangency, in other words, where the shape touches the globe. So imagine taking a piece of paper and a ball, and you wrap that paper around the ball. The location that that paper touches the ball is called the line of tangency. There are many different projection algorithms, but almost all projections are based on one of the three basic types: cylindrical, conical, and planar, also known as azimuthal. So let's take a look at a couple of map projections. The first one is a cylindrical map projection. This is a common projection often used to display the continents on the surface of the Earth. Note, however, that with the cylindrical projection, where the imaginary paper wraps around the globe and then is displayed on the flat surface, you can see where the most accurate line is on that map. It is along the equator, or that line of tangency. Another map projection is the conical projection. So again, imagine taking your piece of paper and wrapping it up as a cone and sticking it over a globe. The line of tangency, where that cone now touches your surface of your sphere, is the most accurate line on the map. Another map projection is the planar projection. Now the planar projection operates on the principle of a point of tangency rather than the line of tangency. Note in this example, the stereographic North Pole aspect is where that plane touches the surface of the sphere. In this case, it's placed at the North Pole, and we can see that the North Pole area is highly accurate, but as we move away from that point of tangency, our accuracy decreases and our distortion increases. Now we'll talk about something that's a little more specific, the universal transverse Mercator. Now the UTM projection was designed to take advantage of the line of tangency and minimize the effects of distortion. It's widely used in the United States for mapping United States Geologic Survey topographic maps, but it's also used in other places around the world. And it can be used in other places around the world because the UTM system divides the globe up into 60 6-degree segments. These segments are called zones. Each zone is 6 degrees wide and is divided by a central meridian and the equator. Now you might be wondering how this limited or small scope could be useful. Well, actually the limited scope of a zone actually helps maintain a high level of accuracy. Some UTM characteristics with which you need to be familiar. Now it's useful to be familiar with UTM characteristics. Again, each UTM zone is 6 degrees wide. There's 60 of these UTM zones dividing the globe. The zone of origin is generally at the equator, and each central meridian is given a value of 500,000 meters. The measurement units for UTM are always in meters. The X and Y values for UTM are called eastings and northings, and UTM coordinates can never be negative. This makes this a very attractive coordinate system. Easting is measured from the zone's central meridian, which again is designated as 500,000 meters. It's also what we call a false easting. The northing is measured from the equator in the northern hemisphere and from 80 degrees south latitude in the southern hemisphere. So just as an example, we have some latitude and longitude points here that have been converted to UTM eastings and northings. Now if you look at the easting and northing, the value for the easting is 621,160.98 meters. Well, how do we get this value? Well, we're trying to plot the location of the Austin, Texas Capitol Dome. The Austin, Texas Capitol Dome happens to be 121,161 meters east of the 500,000 meter false meridian. So if you take 500,000 and you add 121,161 to it, you'll come up with the value of 621,161 meters east. Now, as for the northing, 3,349,893.5 meters north of the origin or the equator. So if you were to step back 3.3 million meters, you would be approximately at the equator. So we combine this XY, this easting and northing, inside of zone 14, and you'll find the Austin, Texas Capitol Dome. Now there are some limitations to UTM, and it's excellent for many different types of studies. However, while excellent for these large-scale mapping within zones, UTM can be very cumbersome when you try to map outside the area of a certain zone or try to map across two different zones. Generally speaking, this shouldn't be allowed. You should never be able to map across two UTM zones. And some different locations have come up with their own method of getting around it. So in Britain, for example, the British National Grid breaks the country into 100 by 100 kilometer squares. In Idaho, for example, which is also straddled by two different UTM zones, they've come up with their own measurement system called the Idaho Transverse Mercator. So different places using different methods have overcome the limitations of UTM while still using the same basic principles. Here in Utah, we extensively use UTM because the state almost completely fits within UTM Zone 12. Since all map projections and coordinate systems have their limitations, and since they're all different, it's important that you understand and know your data. You always need to understand and know what your projection is, what your coordinate system is. If you don't, you can run into all sorts of problems. Quality printed maps will indicate the datum and projection and the coordinate system in the legend. And likewise, any maps you make, it's important to note at least the coordinate system and the projection on your map. This allows people to know and understand what the map was initially measured or created in case they need to go back and make any changes. Speaking specifically of a USGS topographic map, if you look at the bottom right hand corner of any USGS map, you'll note a paragraph of metadata. If you look through that metadata, you'll note that there's indications of what the datum are, both the vertical and horizontal datum, and what the projection is, and other measurement or information you might need to know. So just as an example, the importance of knowing your projection. What you see here are 3 map projections all pinned in the same location. In green, we have an unprojected latitude and longitude. In red, we have a Mercator projection. And in blue, we have a Lambert conformal conic. You can see how each one differs. So you can understand now that if you don't know the right projection or coordinate system, or you try to compare 2 different data sets using different coordinate systems, you can run into problems. So an example from my own research a number of years ago were riparian monitoring sites that were going to be placed on a river, and then aerial photos were going to be captured by an ultralight aircraft. Proper knowledge of the data was unknown at the time of the aircraft flight, and each layer contained a different datum. So the aircraft flew over the points and triggered a camera every time it flew over those points, but those points weren't exactly on top of the river, meaning that each point took a nice picture of sagebrush rather than a picture of the riparian area. This was a costly mistake. Another example of how map projections differ, again looking at the Capitol Dome in Austin, Texas, this graphic shows us datum difference. So it's again always important to know what your datum is, especially if you're out using a GPS. Note the differences in datums depending on what is set and what is collected. It is, generally speaking, possible to convert or transform GIS data from one projection coordinate system or datum to another using tools in the GIS. Luckily for us, these tools are generally automated, although you need to remember that every time that you convert from one projection or coordinate system or datum to another, you'll introduce a bit of mathematical error into your location. To always make sure that all of your data in your GIS projects are in the same projections, coordinate systems, and datum.